So good evening, ladies and gentlemen, and welcome to my talk regarding fatigue of welded joints. And in particular, I will talk about weld ends, which are particularly critical in the mechanical structures. And in this case, we will refer to off-road vehicles. And the method is based on a local approach. We heard about the importance of local approaches this morning in the plenary lectures. And the method I will present is the peak stress method. So the context of my talk is very heavy off-road vehicles. This has been marketed last year, and we have been involved in Padova University for the design and development of the suspension systems, and in particular the rear axle. You see here all partners involved in the project. The motivation for the work is that if we look at the structural side of the vehicle, and in particular to the rear axle, it is built as an assembly of welded parts. And you see here in orange the weld seams. And there are so many weld ends and extremities in these constructions. And we all know that in design standards, it is difficult to find such structural details classified. With that in mind, we were asked to apply the local approach, and we studied the fatigue lifetime of such structures using the peak stress method. The basic idea is to take into account the sharp V notches at weld toe or the weld root, and defining an appropriate design stress. So with these research questions in mind, we followed on parallel tracks both fatigue testing with laboratory specimens and intermediate welds, but also fatigue tests on full-scale structures were performed. Then we calibrated the finite element model with an appropriate prototype instrumented with strain gauges, and we applied the peak stress method, which is now automated in ANSYS. And finally, we transferred this knowledge into the software package adopted by the industry. Now, for time reasons, I will talk just about the peak stress method to give you a theoretical background, the fatigue on specimens, and finally, I will show the automated applications with the peak stress method. So the outlet of my presentation starts from some theoretical background. Let's talk about the peak stress method. First, some stress analysis, then the fatigue model stress analysis. If we consider a welded joint, the basic assumption in the method is to model the weld root or the weld toe as sharp V notches, no weld toe radii modeled in the finite element model. Then with a rather coarse mesh, later on I will talk about how coarse can be the mesh. We have to consider the linear elastic peak stresses at the weld root and weld toe. We have demonstrated that in the K-dominated zone, if you take the maximum principal stress, for example, at the weld toe, and you insert the maximum principal stress in this formula, you can estimate the notch stress intensity factor. So sigma 1 peak is the maximum principal stress at the weld toe. D is the average value of the size of the finite element that you use. 1 of minus lambda 1 is the stress singularity exponent, and the K star Fa is a constant well known based on the type of finite element adopted. So the same can be done for mode 2 stresses in plane shear and out of plane shear. So in the end, if we take the linear elastic peak stresses at the weld toe and weld root, we can estimate all 3 notch stress intensity factors, and this is necessary for treating the multi-axiality. Now, going to the fatigue model, this is the model we adopted. Some of you may be familiar with the average of the strain energy density, which takes into account the average strain energy inside the control volume at the critical point, either the weld toe or root. This is the expression based on the notch stress intensity factor. Now, if you take this expression and you put them inside here, and you define an equivalent uniaxial plane strain state, you come up with the final expression of the equivalent peak stress, which is nothing but an energy averaged inside the volume to take into account the stress gradient effect. All the constants here are published in our paper, so the design engineer must only take the linear elastic peak stresses for mode 1, 2, and 3 at the singular point and enter this formula. All constants have been published. What is the advantage of the peak stress method? It is applicable to complex 3D structures. It does not require modeling of the Weld toe radii. You have not to post-process stress distance data to take into account the stress gradient effect. You just post-process the linear elastic peak stress inside this formula. And you can take into account the constant amplitude as well as variable amplitude loading condition, uniaxial and multi-axial stresses. And above all, we have recently implemented the method in ANSYS. I will show you later on the implementation. Now we have the design stress. We need the resistance curve to be coupled with the design stress. And in the past, we have post-processed, in the past means in the last 20 years, more than 1,000 experimental data. We represented the data in terms of equivalent peak stress, and we came up with two fatigue design curves based on the local biaxiality ratio. As you see here, the local biaxiality ratios weights the shear mode contribution to the linear elastic strain energy to the mode 1 contribution. So if lambda is equal to 0, this means no shear modes in the linear elastic strain energy. For example, pure axial loading, pure bending loading applied to the fatigue of welded joints. You can take a slope of 3, and this is the design curve for different survival probability. As soon as you have lambda greater than 0, so as soon as you have shear modes in the strain energy density, you have to shift to a flatter slope of 5, and this is the design curve we found by fitting experimental data. So now the method is very quickly set up. We have the design stress and we have the resistance curves based on the values of lambda. Now I will talk about the application to our welded details, which resembles the kind of weld ends we had in the off-road vehicles. So we designed this specimen. It is an S355 plate with a hole. We inserted an alloy steel tube inside. This is the section, and we welded the tube to the plate. You see that there is a root gap because the penetration is not complete. So you see here the reference geometry. We have the tube, we have the plate with the hole, we have a partial penetration. So if you consider the sharp V notches, we have the plate side toe, which is a potential crack initiation point, but also the weld toe at the tube side, but also the root. But the root is due to the backlash, is not a pre-crack, it is indeed a slot. So the root has two critical points at the plate side and at the tube side. So in the end, we have potentially 4 points in competition. And this is a very difficult problem to face using the design recommendations, which cannot solve the problem of finding the most critical point among these 4 ones. We designed 2 versions of the specimens, one with intermittent welds, which are almost parallel to the loading direction, and the other one where the intermittent welds are transverse to the loading direction. And this determined the name given to the geometries, longitudinal and transverse joints. So this is the joint geometry. The testing condition was pure axial loading under pulsating tension. And you see here the weld start and stop points with the real geometry. As a failure criterion, we adopted a sort of stiffness drop corresponding to an increase of 0.1 millimeters to the hydraulic actuators. We will see later on what does this mean in terms of crack length. We tested 4 test series, 2 transverse and 2 longitudinal, because we tested the joints both in the welded and in the stress-relieved conditions. And you see here the damage we observed in terms of crack initiation point at the tube side or at the plate side. But I will show this in more detail here. When we satisfied the crack initiation criterion, you see here the crack we observed. This is the transverse joint. You see here the tube. This is the plate. This is a crack emerged from the weld root, but at the same time, we observed some cracks at the weld toe. This is the weld toe tube side. By using dye penetrant, you see better the initiated cracks. So with this failure criterion, the crack is indeed not very short. It is some 10 or 20 millimeters long. And you see multiple crack initiation point. Going to the longitudinal joints, you see that the crack initiation point was always at the weld toe at the plate side. This is the plate, this is the tube. The applied load is vertical, and you see here the crack initiation point, and then you have the crack propagation in the main plate. Now let's start from presenting the data in terms of simply using the nominal load range, no stress analysis at all. Let's start from the longitudinal joints. You see a nice slope equal to 3 according to the standards, and you see that in the finite life, we do not have any advantage of the stress relieving heat treatment, and this has been found also in other research projects. If we look at the transverse joints, things are a little bit different. We see some effect of the stress relieving joints, but I want to bring your attention to another point. Look at the slope. We have a more gentle, more flat slope of 4.5 or 6.3. So flatter than we observed in the longitudinal joints. And people familiar with the fatigue of welded joints, and so as soon as see flatter slopes, thinks that the crack propagation phase is particularly long, and this is the explanation in this case, as I will show later on. Now, we want to correlate with this data using the peak stress method. So we started by acquiring the real weld seams using a laser scanning. You see here in the lab the laser scanning technique. We came up with a step file which was imported in the ANSYS model, and this is the complete model. We acquired both all the 4 weld seams and applied those weld seams to a transverse joint. This is the case of the figure, and also to the longitudinal joints. But we also proceeded with the simplified option of taking an idealized joint with a weld seam with the nominal thickness and with the weld end obtained by the rotation along the weld root point of the hypotenuse of the weld seam. So we have the real scanned weld ends and the idealized scanned weld ends. The stress analysis, according to the peak stress method, has to take into account the peak stresses at the weld toe or weld root. Pointer does not work any longer. Anyway, here we are. So we took the linear elastic peak stresses at the weld toe, plate side, tube side, and also at the 2 point of the weld root, since it is a slot, as we have noted before. So you see here the mode 1 yellow, mode 2 blue, and mode 3 linear elastic peak stresses, which must be input in the design equivalent peak stress we have seen before. Okay, you see here the model with the idealized weld ends. We can exploit here the triple symmetry. So we have just 1/8 of the weld geometry, while with the actual weld ends, of course, we cannot exploit any symmetry plane. Now, I do not want to go into details of the adopted meshing rules. The linear elastic peak stresses at the weld toe and root can estimate the notch stress intensity factors, provided that the mesh is not too large. It can be large, but not too large. Since we have here a very narrow weld root, we have to decrease to a size of 0.4 millimeters according to the design, according to the rules of the peak stress method. These rules are published in this paper. I don't want to go into the detail. We adopted the standard 3D second order tetra elements. The same was done for the real weld ends, and you see here the 4 critical points, as we said before: the weld toe line, on the plate side, the weld toe line at the tube side, and the two, well, the root lines, plate side and tube side. So all these points along these lines are in competition to initiate the crack. After running the linear elastic finite element analysis, the first question is, which will be the crack initiation point? You have so many points in competition, and the first way to test a model, a fatigue model, is to see if it correctly predicts the crack initiation point among those in competition. So we have to plot the equivalent peak stress along all the lines. You see here all the stress fields along the weld toe and weld roots, both with the idealized and the real geometry. If we start from the transverse geometry, you can see that the maximum equivalent peak stress with the reference load is here. This symbol is the weld toe at the tube side. In this case, we have the maximum stress for the longitudinal geometry at the weld toe in the plate side. So weld toe plate side is here, weld toe tube side is here. And if you remember the dye penetrance I showed you before, the crack just started from here and then propagated out of the weld toe. So the peak stress method correctly estimates the crack initiation point. This is the first good news. After that, if we consider the distribution of the equivalent peak stress and the local biaxiality ratio, you see that we had in both cases a very, very low value, close to 0. So we adopted the design curve for pure mode 1, the one with slope equal to 3. Sorry, I went forth and I have to go back. Here we are. Here we are. This is for the situation for the transverse joint geometry. This is the situation for the longitudinal joint geometry. You see the fatigue life and the equivalent peak stress. This is not fitted on the experimental results. This is a validation. So this is a pre-existing design curve. If correlation were perfect, the experimental data point should lie in the 50% survival probability line. We are not exactly there, but we are inside the scatter band. We are very much on the safe side instead for the transverse geometry, and we wanted to investigate a little bit this, because after processing more than 1,000 experimental results, this situation was quite new for us. And the explanation came from here. This is the specimens we tested until the crack initiation criterion was satisfied, plus 0.1 millimeter to the hydraulic actuator, and we proceeded the fatigue test until the final separation. You see a very long fatigue life if compared with the same situation for the longitudinal geometry. And the reason for that is that for the transverse geometry, indeed, we were tested two welded two structural details in parallel. If you consider the stress flow, coming to the welded joints, the stress flow can follow the next section in the plate or can engage the weld seams and enter the tube. Now, when the crack starts, when the crack initiates at the tube, the stiffness of the tube decreases while the stiffness of the plate is the same. So with in the course of the fatigue test, we have a decreasing stress flow engaging the weld, even though the crack length increases. So the resulting stress intensity factor is more or less constant. We have proved that with dedicated calculations. So to test if this physical interpretation was correct, we simply cutted the net section and we tested a new joint. If this reasoning is true, now we tested simply a welded joint where the stress flow has to engage the welds because we do not have a structural path through the plate. And doing that, you see that the joint came into the design scatter band. So in conclusion, we successfully tested the transverse and the longitudinal geometries, and in the end, we predicted the crack initiation point and the fatigue life with that correction I have shown. In the future, we will test the again, the idea, we will perform crack propagation tests, and this is our user interface in ANSYS where the method has been implemented, and starting from this year, the software is also marketed. Thanks for your attention.